We start our lesson. Today is theme 10. Please write down to your notes the theme of our lecture: basics for designing machine fixtures. Basics for designing machine fixtures. And a plan of our lecture. 10.1 Pupils and classification of technological fixtures. 10.2 Attachment fittings of technological fixtures. And 10.3 it's fixture clamping devices. Please write down to your notes the theme and plan of our lecture. So, item 10.1, Pupils and classification of technological fixtures. Fixtures are called auxiliary technological devices used in machining for installing and fixing manufactured parts or tools, weeding tools, etc. And please write down this century about fixture. What is the fixtures? The use of fixtures significantly simplified the work of the worker, increases his productivity, and expands the technological capabilities of the equipment. With the help of fixtures, it is possible to increase the accuracy of processing, since the workpiece being processed during installation takes a more accurate position in relation to the elements of the technological system. The cost of designing, manufacturing, and operating fixtures is from 3 to 7% of the cost of manufactured parts. The use of standard parts and assemblies of fixtures make it possible to reduce the cost of the manufacture and design. Fixtures are classified by technological or target, pupils, and degree of specialization. For purposes of attachment of mechanical processing, fixtures are divided into the following groups. For installation and fixing of parts of blanks of workpieces. For fixation and fastening of working tool. Straight to the tool in the processing process. Detail control, hardening, moving, and tuning over the tuning of workpieces. Machine fixtures are divided into groups according to the types of machines on which they installed. Tuning machine, drilling machine, milling machine, etc. And now we can look a video about fixtures and what is a fixtures. What is a fixture? It's our first video today. What is a fixture?
Metal parts created by casting, forging, or other metallurgical processes often require machining operations prior to being ready for service. The casting in this example is a housing for a worm wheel gear. The example here specifies that a boring operation will be performed. The part must be secured so that no shifting or movement occurs during machining. The process of securing the part is known as fixturing or work holding. Clamps, supports, and other components are used to create the overall fixture. This example shows a single housing part on a single fixture. Once fixtured, the boring operation can be completed. Larger setups, such as this square pedestal fixture, are capable of holding multiple parts at the same time and rotating as needed. Naturally, this type of setup is preferable for high-volume operations. Like many processes involved in mechanical engineering, fixturing is an extremely important step that must be performed correctly in order to maximize profits and efficiency.
So, according to the number of workpieces or tools installed at the same time, fixtures divide into single and multi-place. According to the degree of specialization, there are universal fixtures, specialized or group fixtures, and special fixtures. It's according to the degree of specialization. Universal fixtures, vices, dividing heads, prisms, cartridges, etc., are used in the manufacture of various types of parts. Specialized fixtures are used in the manufacture of the same type of parts of different sizes. And special fixtures. Special fixtures are used for processing in one operation or for processing one surface. So please write down to your notes another part of classifications of fixtures. Another video that I want to show to you, it's about fixtures too, of course. 10.2, video 10.2.
Used.
What are fixtures and work holding devices for horizontal machining centers?
HMC operations require the workpiece or workpieces to be firmly secured during machining processes. Workpieces are secured using work-holding devices or fixturing devices. The most common work-holding devices are vices and fixtures. Irregular fixtures also will be addressed. The purpose of holding a workpiece is to secure a reliable contact between the workpiece and the locating elements being used. To locate a workpiece is to establish its position in the axis coordinate system. and to ensure that the work holding devices used can withstand the required cutting forces. Proper location prevents displacement of the workpiece and vibration during machining. It also ensures machining accuracy and the correct position of the workpiece relative to the cutting tool. The workpiece is located on suitable surfaces, edges, or bores. The suitability of the surface depends on the geometry of the part. The workpiece could be located on a flat surface, resting on points, or located using a variety of other requirements, such as a serrated surface for holding rough castings and forgings.
And before we start item number 10.2, I want to show to you the third video. Jigs and fixtures. The difference between jigs and the fixtures.
Let us see the 3D model of a typical jig. A jig is a metal.
It's a typical jig, 3D model of the typical jig.
Working tool used to hold the workpiece and to guide the tool during machining operations. Let us see an application of jig in drilling operation. Here, the jig holds the workpiece and also guides the tool to drill in correct position. Leaf jig. Let us see the 3D model of the leaf jig. Leaf jig is an open type jig in which a leaf or a plate is arranged to swing about a hinged point to load and unload the workpiece easily. Vise. Let us see a 3D model of a vise. Vise is a mechanical screw apparatus used for holding or clamping the workpiece. Turning fixture. Face plate is one of the turning fixture. Let us see the 3D model of the face plate and its purpose.
And one more video. For quick workpiece setup, we use fixtures. One-touch clamps serve for various applications in machine assembly, testing, and inspection in different industries. It's automobiles, industrial machines, office machines, semiconductor parts, audiovisual apparatus. Okay, we start item 10.2. Have your questions about item 10.1, pupils and classification of technological fixtures? I understand what is the fixtures. Okay, you have the questions. So 10.2, attachment fittings of technological fixtures. Attachment fittings of technological fixtures. The setting elements of the fixtures, you can see in figure 10.1 the settings elements. 1, 2, 3, and another. Of the setting elements of the fixtures serve to give the workpiece the correct position relative to the cutting tool. Consider typical cases of workpiece, installation and design features of the installation elements. When installing the workpiece on a plane, constant adjustable self-aligning supports are used. Those that are supplied. Permanent supports include different designs of pins and base plates. To install workpieces on raw surface, pins with spherical or corrugated head are used. You can see it and at picture and figure 10.1 A and B. The latter and are used to install large castings and forgings. Pins with a flat head in figure 10.1 C are designed for installation on a plane machined not lower than RA 2.5 micrometers, its parameter of roughness. Blanks with cleanly machined base, the surface is mounted on the support plates. It's figure 10.1D. Permanent supports change when worn. Adjustable supports, unlike permanent ones, allow you to, excuse me, wait a minute. Permanent supports change when worn. Adjustable supports, unlike permanent ones, allow you to periodically change their axial position to compensate for the wear of the contact plane of the supports. In this regard, adjustable supports are mounted in the body of the device by screwing into the body on the thread with the lock nut fixed. The resistance in the body of the fixture are gently arranged according to the 6-point rule. Installation elements used as additional supports to eliminate deformation of the workpiece from the action of cutting forces, clamping forces, or the own weight of the workpiece are performed in the form of self-installing or raised supports. An example of the construction of a self-alleging support is shown in figure 10.2. You can see in this figure this example. Workpiece 1 is installed on permanent supports, pins or plates. However, in order to exclude the deflection of the workpiece, an additional self-adjusting support 3 is used. This support, under the influence of previously compressed spring 5, is pushed up until it stops in the surface of the workpiece, after which its position is fixed with a screw 4. The cap 2 protects the device from the impact of small chips. These caps 2, protect the device from the impact of small chips. For large-sized workpieces, wedge supports are used, which are brought in with which are locked by tightening the hand well. Support pins and plates are made of steel 45, U8A, steel 20 or steel 20X, followed by head treatment to a hardness of 56 or from 56 to 60 HRC, and grading of bearing surfaces to RA 0.63 micrometers. When installing the workpiece on the outer cylindrical surfaces, prisms 2, like in figure 10.3, cartridges and bushings are used. Prisms are usually produced with an angle alpha is equal 90 degrees. Angle alpha. It's usually equal 90 degrees. For precise installation of the prism on the fixture body, pins 3 fix the prism with screws 1. Chucks. Before we start this slide, we can see a video about chucks. So,
wiki.ezvid.com. Search EasyVid Wiki before the 7 best lathe chucks. Let's get started with the list.
Chucks.
Starting off our list at number 7. The internal jaws on the WEN LA4444 can clamp down on tenons between 1.6 and 2.8 inches, while the external jaws can expand against recesses between 2 and 3.2 inches. It comes with a screw chuck for additional support. This is a very affordable option and made from durable cast iron, but it doesn't include a wrench for the screw chuck. Number 6. The Woodstock D4054 is a 3-inch model with 4 reversible stepped jaws for both internal and external gripping. Setting materials is easy thanks to its knurled adjustment plate and the 2 4-inch wrenches included for final tightening. This one's suitable for round and square work pieces and is backed by a 1-year warranty. However, the narrow jaws are not ideal for wood. Coming in at number 5 on our list. The 4-inch LLD Cymex self-centering is rated to clamp down on pieces almost as small as 1/4 of an inch and almost as large as 2.5 inches. It offers a maximum turning speed of 3,000 RPM and a thread depth of 25 millimeters, and it comes with T-handle Allen wrenches. Newest choices can only be seen at wiki.easyvid.com. Go there now, and 3 Harden 11 has a cast iron body and 3 hardened steel jaws that score between 58 and 62 on the Rockwell C scale. They're kept to within 0.002 of an inch of perfect alignment with each other thanks to a high precision bevel gear. This one's available in 6 and 8-inch models with reversible jaws. It can accommodate almost 8 inches. Nearing the top of our list at number 3, despite a relatively small size of 3.35 inches, the Nova TK48246 direct thread can spin bowls as big as 14 inches and spigots as long as 6 when it's outfitted with 50mm jaws. It's compatible with all the company's accessories. It's equipped with an anti-release spindle lock, copper-impregnated jaw slides, and a hard-shell storage case. At number 2, considering that it comes with 4 sets of jaws, the PSI Woodworking Barracuda CSC 3000C is reasonably priced and a good first purchase for new users looking to try their hand at wood turning. It comes pre-threaded for 1-inch spindles. It features a 3/4 inch adapter and a plastic carrying case, and is backed by a 2-year limited warranty. And coming in at number 1 on our list, while the Easy Wood Tool C1000 is somewhat pricey, the impressive design enables you to clamp down on projects using only your fingertips and switch out sets of jaws within seconds. Its 1 3/8 of an inch tenons have a 2-inch expansion range. It comes with 3/8 dovetail jaws and an instructional manual and DVD. It's designed and made in the USA. Newest choices can only be seen at
And another types of chucks. This video, we need another video. Mechanical chucks.
My name is John with CN Modification Langston. Pattern allowing them to fit all 4 of the most common roll stand models in the US: DHS, Marquardt, Martin, and Langston. We have another easy install feature already built into the design right from the beginning. In the side of the flange, we have a hole cut in here for an RPM counter, if you need to have a sensor or magnet built in for your RPM system. Let's have a closer look at some of the chuck's remarkable features. Our standard jaw design features serrated expansion units. So by implementing the serrated jaw and creating an extra large contact area with the expansion units, we can easily grip worn and recycled cores. This means we can reduce slippage and dust and core debris created by core slippage. Our chucks also can be equipped with smooth or carbine-coated expansion units to fit your specific application. Your local CST rep will be happy to help you figure out what jaw option is right for you. Our jaws expand more than a 1/2 inch, so if you have an oval core or one that is otherwise out of round, this high expansion rate will compensate for that and make sure you get firm contact with the core. Our chucks are designed for American cores. That means that our 4-inch chuck is a 4-inch chuck and not a 100mm chuck. A 100mm chuck is only 3.94 inches. That may not seem like a big difference in size, but when you have a chuck that has a snugger fit to the core from the beginning, you're able to get full engagement faster and increase your splicing speed without sacrificing web tension. Earlier, I spoke of our focus on providing a chuck that is designed to be easy to install. Now, more importantly, let's look at how our chuck is designed for easy use and simplicity of maintenance. We keep your plant maintenance team in mind. 3 components. That's it. As you take our chuck apart, you may notice right away how short our center bolt is. Why is that? Because our flange is made from one piece of forged steel. It's not bolted together or spun weld. This means our flange is inherently strong, and we don't need to compensate for soft metal and breakage points with extra long bolts and pins. You don't need to worry about our flange cracking under weight or pressure. Now let's look closer at our expansion units. I already identified our high rate of expansion and serrated jaws. We have extra thick tabs to make sure you don't need to stock replacement expansion units. Ours hold up for years. We also feature a simple embedded roller design. This roller allows the expansion unit to automatically center itself in the best possible location on the center cam. And you don't have to worry about lining up pins and rollers that fall out if you remove the chuck on the roll stand, or having additional contact points for dust to get caught in and cause core burnouts. The chuck housing itself is one piece. No joints that allow dust to build up inside of the chuck or places to get paper stuck. It has both sealed and greased bearings designed to withstand any level of side pressure your operators may use when aligning the roll stand arms. If you need to perform any maintenance on the Renova chuck, you can easily do so on the roll stand. No need to cart it back to the shop and sort out all those little parts. With our simple, reliable design, we are able to help our customers achieve consistent tension at any run speed with little to no maintenance. We offer several other models beyond our standard chuck, including ones like this one here. This is our WR1 chuck, designed for roll stands with built-in core ejection systems. Aside from sharing our simple, robust internal design, this chuck also features new waste-reducing features, like a double chamfer on the expansion units. This means smooth corners all the way around, so there's no chance of the expansion unit snagging on or tearing a core. Our core ejector plate is made from aluminum with a nickel coating, rather than steel. This means it's lighter. Why is that? It builds up less inertia, so while it still easily pushes off the heaviest rolls, it doesn't build up as much force and become a safety risk if the roll stand ejector arm gets stuck or malfunctions, which can be a problem with some OEM ejector arms. Another waste-reducing feature of this chuck is the cutout runout ring here at the bottom. This is designed to keep operators from accidentally chucking up too far. It makes sure that the chuck makes contact with the core and not the roll or the paper. If you have manual roll loading, this helps stop operators from using too much side pressure and chucking up past the core and into the paper itself, reducing paper waste and helping plants achieve their goals of running the roll all the way down to the core. We stock a variety of chucks designed for thin-walled cores, different size cores, extended or reduced nose cone tapers, or for other roll stand manufacturers beyond the big 4. Don't have a standard application? No problem.
So chucks are can 2, 3, and 4 jaw collect, membrane, and other designs. On figure 10.4 shows the structural diagrams of collet chucks. When clamping the workpiece, the collet is drawn into the conical socket by a draw pipe, figure 10.4a, or inserted into the cone, figure 10.4b. Figure A, 10.4a, and 10.4b. Collets are made of U10A steel. Cam and collet chucks simultaneously perform the functions of centering or setting the workpiece and clamping device. Collet chucks. I have a video about collet chucks. 10.6 mechanical, 10.7.
Turning is to grip internal diameters from 1/8 inch up to 4 inches. The spindle mount style mounts directly on certain ANSI and ISO A2 spindles. A drawbar adapter is required to actuate the collet. 5C, 16C, and 3J collet-style systems mount directly in a hard-inch turning center, manual lathe or rotary indexer, or in a collet adapter on a chuck-style lathe. The Sure Grip arbor system is designed for use on grinding machines and lathes. The arbor can be held between centers or chucked on one end and supported by a center on the other end. Hard-inch guarantees that when the expanding collet is mounted on the arbor, the TIR of the collet and the arbor will not exceed 5/10. This is a Sure Grip expanding collet system that we will install in a hard-inch turning center with a collet-ready spindle. Open the drawbar access door of the hard-inch machine and remove the locking bolts to loosen the machine's drawbar. Unscrew the draw plug from the end of the arbor and slide the collet over the arbor, aligning the collet keyway to the key on the arbor. Screw in the draw plug to secure the collet in place. Align the collet keyway to the spindle key and slide the assembly into the spindle. Return to the drawbar access door and turn in and tighten the locking bolts. The gripping range of each collet is plus 15 thousandths from its specified size. This part has an inside shoulder that positions it on the expanding collet. This example does not achieve dead length because the collet moves. Exact part length is achieved by locating the part against the face of the arbor or against a machinable dead length work stop. This provides an extremely stable part so that deeper cuts, finer surface finishes, and closer tolerances can be achieved. Here we show the workpiece located against the face of the arbor. A work stop is not necessary. In this example, a standard work stop is bored and faced off to accommodate this multiple step workpiece. This is an example of a short gripped workpiece using a dead length work stop to machine the part to a desired length. In addition, the work stop acts as a limit ring behind the part based on the short gripping length. When the workpiece is larger than the standard work stop diameter available, a custom work stop can be machined for your required application. Hard-inch Sure Grip expanding collet systems can be custom manufactured for special applications for spindles, sub-spindles, and mill tables. Pickoff collets are frequently engineered for Swiss and multi-spindle machines. Sure Grip expanding
It was information about chucks. If the basic cylindrical surface of the workpiece is made with a deviation corresponding to 6 or 8 IT grade, then the part can be installed in the sleeve. On figure 10.5, shows the installation of the flange part 1 in the sleeve 2, based on the cylindrical surface and end face. If the workpiece is oriented along two outer cylindrical surfaces, like in figure 10.6, two cylindrical outer surfaces, diameter 1 and diameter 2. Then one surface is based on a prism 1 and the other on a self-aligning prism 2. The use of self-aligning prism is due to the fact that the initial blanks or workpieces are made with certain deviations of geometrical dimensions. To install the workpiece on the inner cylindrical surface and a plane perpendicular to its axis, fingers and for each are used. On figure 10.7, A and B shows constants, and in figure 10.7, C and D replaceable fingers. It's constant figures and replaceable figures. The basing of the workpiece is carried out with a hole on the finger and the end surface of the workpiece on the base plate of the fixture. The base plane of the workpiece must be finished. When installing the workpiece on two holes, two fingers 1 and 2, like in figure 10.8, finger 1 and finger 2, of which one is cut off as shown in the figure. These cuts compensate for errors to delta in the distance between the axes of the workpiece holes to be installed and the same time provide minimal angular deviations of the workpiece around the axis of the cylindrical pin. The calculation of the configuration of the cut finger is given in the reference literature. The diameter of the cut finger is performed with a feed in the hole H7 by F7 or H9 by the D9. Only its small letter must be. Under the line parameters of the hole, above the line parameters of the hole, big letter used. Under the line we use small letter, it's parameter of the shaft. Or H9 by D9. A finger with slices is also used when installing the workpiece along one machined hole and a plane parallel to it. In this case, the cuts of the finger compensate for the fluctuations in size A. Like a figure 10.9. By design, the mandrels are rigid and expandable in figure 10.11. On figure 10.10a shows a cylindrical border of the center type on which the workpiece is mounted with tension under a press. And in figure 10.10b, mandrel on which the workpiece is installed with clearance and tightened from the end with a nut. On figure 10.11a shows a collet expanding mandrel. When the nut 5 is rotated, the collet sleeve C, which has 3 cuts, moves on the conical surface of the mandrel 4. Conical surface. Centers and clamps the workpiece to. Not one limits the movement of the collet to the left. Expanding mandrel shown in figure 10.11b. Having an elastic sleeve 1. This sleeve bursts from the inside with hydroplastic 2. As a result of tightening the screw 3. Tuning the screw counterclockwise release the workpiece from the clamping force. The base hole of the workpiece must be machined with a deviation of at least the 8th grade, IT grade. Expanding mandrels are also available with 3 crackers expanded by an internal cone with roller, bushing, and other designs. Have we a video about this type of fixture? 10.7. It was last. About mandrels.
C and 3J palette style.
We haven't any more videos, so we continue. Figure 10.12. When processing shafts based on center sockets or conical chamfers, centers are taken as settings elements. On figure 10.12a shows the design of a conventional rigid center in figure 10.12b installation of the workpiece with a conical chamfer on the cut center. In figure 10.12, the design of the rotational center, and in figure 10.12g, the design of the drive center with small teeth that are capable of transmitting torque by inserting them into the base conical chamfer of the workpiece. This center designs cause locating errors when obtaining axial dimensions due to inaccuracies in the execution of center pockets or base chamfers. For precise installation of the workpiece along the length, the design of the floating front center is used like in figure 10.12d. When the blank is pressed by the rear center, its end rests against the end of the cone bushing installed in the spindle bore, which ensures the constancy of the axial position of the processing batch of workpieces. And now 10.3, fixture clamping devices. Clamping devices are designed to create a reliable contact of the workpiece with the mounting elements of fixtures and prevent possible displacement and vibration of the workpiece during the operation. When designing a clamping device, the required clamping force must first be calculated. To do this, outline the workpiece installation scheme and determine the direction of action of the cutting force and the clamping force. So please write down to your notes about clamping device. What is the clamping device? This part of the slide, write down to your notes. And we continue. Consider the method for calculating the clamping force for some processing schemes. On figure 10.13, it shows the components P suffix 1 and P suffix 2 of the cutting force P1, P2, and figure 10.13a, B, C, D, and E. P1, P2, P1, P suffix 2. The force it's components of cutting force. Component P suffix 1 is directed against the lower supports. Component P suffix 2 tends to move the workpiece. Workpiece shift will be excluded if the inequality 10.1. Please write down this formula to your notes. In this formula, f suffix small f suffix 1 and small f suffix 2 are the friction coefficients of the workpiece against the clamping and setting elements of the fixture. So please write down to your notes the formula 10.1 and the figure 10.13a.
Okay.
And last slide. Entering the safety factor K more than 1, we find the value of the clamping force, and we use the formula 10.2. Write down to your notes this formula. Friction coefficient F can be taken when installing the workpiece on flat supports 0.16. F will be equal 0.16. When installing untreated surfaces on supports with a spherical head, 0.18 from 0.18 to 0.3. When installed on supports with a corrugated head, 0.7 or more, its coefficient F is equal, will be equal 0.7 or more. The coefficient K depends on the specific conditions of processing and fixing the workpiece and ranges from 1.5 to 8. That is in fairly wide range. A significant influence on the value of the coefficient k is exerted by processing a workpiece with noticeable surface irregularities in the draft mode, increase in cutting force due to wear of the cutting tool, fluctuations in the developed clamping force, instability of the location of the contact points when installing the workpiece on the slots. So write down to your notes the formula 10.2 and the values of the coefficient of the friction coefficient F. Our time is finished. So we finished our lesson. Have your questions?
No, teacher. No.
Okay, you have the questions. You can find this presentation in our Telegram group.
Okay.
So for today, goodbye.
Goodbye, teacher. Thank you for your time.
Next week.